Hello, calculus students. Um, Hope the quiz wasn't too bad yesterday. Let's get started on continuing those geometric applications of integration. So we're going to do volumes by rotation, the disk and washer method. But before we do this, I want to do a review problem because it's been a while since we've done any of these things. So we're going to do a volume by slicing problem first for practice. So here it is. The base of a solid is the region bounded by y equals cosine x, y equals 1/2 x, and the y-axis. Slices perpendicular to the x-axis are semicircles. Set up an integral to find the volume of the solid. Evaluate it using your calculator. This is going to be a calculator problem. I don't want you to try to do the integral by hand. It's a mess. Just use your calculator function. So pause the video here for 5 minutes. Work on this together. Don't slack off. I'd like to say I'm watching you, but I'm not. Somebody else is watching you. And see if you can remember how to do this. So pause for 5 minutes here. All right, so let me show you my solution. So I know cosine x starts up at 0, 1 and hits the x-axis at pi over 2. So that's a sketch of cosine x. And then the line y equals 1/2 x passes through the origin and slopes up and hits it at some point. I don't know what that point is off the top of my head. And then the third boundary is the y-axis itself. So we're looking at this region. That's the region that's being described here. That's the region that touches all three of those curves. Y-axis here, and cosine x, and y equals 1/2 x. So I labeled everything here. We're going to need that point of intersection. And so I used my calculator function and see that point of intersection is 1.030, 0.515. The equation you get, cosine x equals 1/2 x, actually can't be solved using any sort of algebraic methods. You just have to use a calculator to get an approximation to where those two curves cross. So, slices perpendicular to the x-axis are semicircles. So there's one of my slices. It's perpendicular to the x-axis, as you see. It's going straight up and down. Its thickness is therefore dx. We need to figure out what the volume of the slice is so we can integrate it. So we're told that the slices are semicircles. So I've drawn a very elaborate semicircle. The base there is s, and it's the same length as this slice here. This length is this length. And we know the area of a semicircle is pi over 8 s squared. So I need to work out what s is. Oops, didn't want to do that. I need to work out what s is in terms of x, because my slices are dx. So I need the distance from here to here as a function of x. So that distance, I've got the y top up here and the y bottom. So that length s is y top minus y bottom. And I already have those written as x, as functions of x in the problem. Y top is cosine x. Y bottom is 1/2 x. So that's my length of s as a function of x. As the slices go back and forth across this region, their length changes, and this function is giving their length as a function of x. So, what's the volume of my slice? Well, it's pi over 8 s squared times dx, the area times the thickness, and we know what s is, and so I get this horrible, ugly-looking volume of the slice. Pi over 8 s squared dx, where s has been replaced with my formula for s right over here. So now I need to integrate this. So where do my slices begin and where do my slices end? Well, they begin at the first value of x where I have a slice. That's over here clearly when x is 0. And the slices will pass through the region, and then our last slice is over here when we hit this point. And the x-coordinate of that point, which is what I care about here, is 1.030. Those are my limits of integration. And then I just integrate that solid, or I integrate this volume formula across the whole region to get the total volume of the solid. This is a horrible, horrible antiderivative to try to work out. You get cosine squared and parts. It's just a big mess. So this is why we have calculators. Calculator tells me this is 0.168, which seems pretty small, but if you think about it, there are just semicircles above here. It's not real tall, and this region almost fits inside a square. I mean, this is 1.030, so like there's a unit cube out around here, which would be volume 1, and this is much, much smaller than the unit cube. There's this little semicircles hiding inside this region. So anyhow, That's the answer to the warm-up question. Moving on. And again, pause if you need to write something down, or you can watch it again. It's on YouTube, and there's links on the website. Moving on. So, volumes of rotation. We're starting. We got two main methods. We're learning the first one today. But the idea is, you've got some region. I've drawn this odd-shaped looking region here. It looks something like a flag when I put it. And then we have this axis of rotation. We're going to rotate in space this region around the axis, forming a solid. So you don't have to be able to draw these very well. This one looks vaguely something like this if I rotated around that axis. I don't know what I'd call that. But you don't need to be concerned about having to draw a good picture of what the thing looks like. What you need to be concerned is to be able to understand what does it look like when a slice of the region is rotated. So if I take a slice of this region horizontally here, if I were to rotate this slice, I'd get a disk. It'd look like this. This disk is just a filled-in circle. And so that's fairly easy to understand. I know how to get the area of a disk. It's just a circle. So today, we're going to be looking at when we take our slices perpendicular to the axis of rotation. When we do that, slices are either disks if the region touches the axis of rotation the entire time, then there's no hole and you always get a disk. Or it may be that the region is separated out here from the axis of rotation, and then you'll get washers. You'll get a disk with the hole in the middle, and we'll see some examples of that. So if that's not entirely clear right now how you get this shape, it's coming. So this is the disk or washer method. And you use this when the slices are perpendicular to the axis of rotation. That's important. That this method is when you're making your slices perpendicular to the axis of rotation, like I illustrated here. Horizontal slice, vertical axis of rotation. So let's see our first example. All right, here it goes. Scribble, 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 scribble. A solid is formed by rotating the region bounded by y equals e to the x equals 0, and x equals 1, and the x-axis. So there's my region around the x-axis. So I'm going to rotate that region around the x-axis. And we're going to determine the volume of this solid. So first, let's sketch the region. So there's y equals e to the x. That's that exponential growth curve. This point right there is 0, 1. There's x equals 1. That's one of the boundary curves I've given. X equals 0, of course, is the y-axis. And then the other boundary curve is the x-axis. So here's my region that we're going to rotate. So I'm going to label some things there. There's x equals 1. And this is when I draw my pictures. This is how I will indicate the axis of rotation. I'll draw a little arrow spinning around it. So that will be a sort of visual cue. So that's my axis of rotation. You don't have to draw that, of course, but this is what I'm going to do when I'm presenting these things. So this region here is going to be rotating around this way, like that, making a solid. And we're going to get the volume of that solid. We don't have to be able to draw a good picture. We just need to understand what happens to a slice. So when we rotate it, it will pass through the plane of the page here again. So this would be the other side, sort of mirror image of this. But again, you don't need to understand that. You need to understand, all right, there's a slice. Slice is perpendicular to the axis of rotation. Horizontal axis of rotation, perpendicular slice. When I rotate that, I get disks. The thickness of these disks are dx because they're perpendicular to the x-axis. That's how thick they are. And we're going to have to determine the volume of this disk as a function of x, therefore, because my integral is going to need to be x's. Well, the volume of the disk is easy. It's the area of the circle times dx, pi r squared times dx. And hopefully this is pretty easy. Hopefully this is clear to you that the radius here is always just e to the x. It's this curve. Y equals e to the x. So it's a function of x. The radius is just e to the x. So that's what I write in there. I replace r with e to the x. So that's my formula for the volume of the disk. Now I want to integrate that to get the volume of the solid. Where do my slices begin and end? Well, they start over here when x is 0, and then the slices go through the region, and they end up over here at x equals 1. So those are my limits of integration. There's my formula for the volume of the disk. I'm going to add up all those disks to get the volume of the solid. This might be a little scary, but remember that power to power you just multiply, so that's just e to the 2x. Use fundamental theorem. Antiderivative of e to the 2x is 1/2 e to the 2x. So that's why I get pi over 2. I'm going to plug in 0 and 1, plug in 1, then plug in 0 and subtract. When I get that, I get, excuse me, pi over 2 times e squared minus 1, e to the 0 being 1. So that's that problem. So again, pause if you need to jot something down or ask quick questions. I'm going to move on here. So I'm going to abbreviate these problems now. I'm just going to give you the region, and I'm going to give you the axis of rotation. And it's understood, all of these problems, you are going to be finding the volume when this region is rotated around this axis. So I'd like you to try to set this one up. I'm going to give you a couple minutes to sketch this, and together at your tables, see if you can figure out what the volume of the slice would be, how you would slice this, and figure out what the radius, you get your pi r squared is. So pause for 2 minutes here, see if you can do this. All right, so let's see what I did. So here's my sketch of the curves. I've got y equals x squared plus 1, y equals 10. My axis of rotation is the y-axis. And the trick here, it's not really a trick, it's just you have to be on your toes, be paying attention to what's going on. The method we're learning today, the slices have to be perpendicular to the axis of rotation. So since my axis of rotation is horizontal, my slices need to be vertical. And if you were trying to do it this way, you're never going to get it. We don't know how to do that method yet. So the slices have to be perpendicular to the axis of rotation for the method we're learning today. So that means my slices, oh, there it is, rotate the slice. So I'm going to get a disk. We knew this already. So my slices are thickness dy. That means everything's going to have to be x as a function of y. Everything's got to be in terms of y. I don't want it y equals function of x. I want x equals function of y. So that means this over here, this part of the parabola is x equals the square root of y minus 1 when I solve this. This part we don't care about because the radius is drawn to the right. This part is minus the square root of y minus 1 because over here this is where x is negative, over here this is where x is positive. So the volume of the slice, again, pi r squared dy, and my radius, the distance from here to here in terms of y, is square root of y minus 1. So I have pi r squared, and then in the next step, r has turned into square root y minus 1. And then it's square root. Very nice, because I've got the square root, and then I get to square it, which means the slice is linear. The function is linear that I'm going to integrate. Pi times y minus 1 dy. So, what's the volume of the solid? Well, I need to add up all my slices. Now, where do my slices start and end here? Remember, we're doing dy. dy everywhere here. So I need to say, okay, so at what y, what's my lowest y, and what's my highest y for my limits of integration? Clearly, my highest y is y equals 10. That's this right here. That's my slices go up, 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 and then they'll stop here at y equals 10. Down here at the bottom, this is y equals 1. You can work that out pretty easily. This is the point 0, 1. So that's y equals 1. So my slices go from 1 to 10. Excuse me. And so now I integrate. So boom, 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 working a bunch of stuff out, hammering out through my integral, 40.5 pi. I know that went really fast, so you can copy while I talk. Took the antiderivative of y minus 1. The pi just gets to sit there. Plug in 10, plug in 1, I get this. Works out to 40.5 pi. So again, you can pause if you want to copy down these things. It's available to watch again later, so I'm going to move on. Now, washers. We talked, sometimes you're going to have washers. Watch this when the slices are still perpendicular to the axis of rotation. That hasn't changed. But now the region doesn't touch the axis of rotation. Now, what I mean doesn't touch, it might touch at a point, but it's not in contact with the axis of rotation for the whole region. All the other ones we've seen, the region that we're rotating is actually sitting on the axis the whole time. So there's never any gap. Let's look at this one, though. So the region is y equals x and y equals x squared, and we're going to rotate around the x-axis. So that's not too difficult to draw. It looks something like this. So we've seen this before. Y equals x squared. It's a standard parabola. Y equals x is a line with slope 1, passes through the origin. So that's the region. That point up there where they cross is 1, 1. And we're going to rotate this around the x-axis. So now we see here that the region is not sitting on, the region is no longer sitting on the axis of rotation. The region's up here, floating up. The axis of rotation is down here. So we need to take our slices perpendicular to axis of rotation still. So they're still going to be vertical. Horizontal axis rotation, vertical slice. I keep emphasizing this so you can see the perpendicular sign. But now when I rotate this about the axis, rotate my slice, since it doesn't contact the axis of rotation, I get a hole. There's this washer shape here. This area is going to be the larger circle minus the smaller circle for this washer. Hopefully it's clear why the hole is there. Here's where the slices are farthest from the axis, but then there's the slices near to the axis here leave a hole because it doesn't contact the axis. So we need to determine the volume of this slice. Again, the thickness is dx, so everything's going to have to be written y as a function of x, which they are. That's good. Everything's the way we want it in terms of that. So what's the volume of the slice? Well, hopefully it's clear. Pi r big squared, pi r big squared is simply the area of the larger circle. R big is going to be the larger radius. And then we have minus the area of the smaller circle, the circle inside here. And then we're going to multiply by the thickness dx. So I need r big and r small in terms of x. So what is r big? Well, r big is from the axis up to there. I've done it in green there. So that distance is from 0 down here up to y equals x. So that means that distance is x minus 0. Now, it seems silly to put in the minus 0, but I'm putting there for the next problem that we're going to do, where it's useful to think that way. Now, next I need the smaller radius. I need r small. So what is that going to be? Well, that's in there. It's kind of hard to see. Everything's all crammed in there. There's a small little bracket right there. That's r small. That's the smaller radius. So that's the distance from 0 to this curve, which is y equals x squared. So we're going to have x squared minus 0. So then here's my volume of the slice. This is just pi r squared minus pi r squared, but I've replaced r big and r small with the green radius and the purple radius, the bigger radius and the smaller radius. So now we're going to simplify this mess and then integrate across all my slices to add up their volume and get the volume of the solid. So the volume so this simplifies to pi x squared minus x to the fourth, still dx. Have to add them up. Add them up by integrating. Slices start over here when x is 0. Go through the region. They end over here when x is 1. Those are my limits of integration. And so that's the integral. And I'll leave it for an exercise. You can work this out. I'm not going to work it out in the video. You should get 2 pi over 15 when this is all done. So, again, pause if you have any questions. You want to copy something down. Move on to the last example. Region same, but now I've moved the axis of rotation over to x equals 2. This is obnoxious. There's my region again, but x equals 2 is over here. It's a vertical line. It doesn't even contact the region at all. This is the point 1, 1. X equals 2 is over here someplace. This is not necessarily drawn to scale. It doesn't need to be perfectly drawn to scale. Excuse me. So, since my axis here is horizontal, I'm going to need to take vertical slices. There's a slice. When I rotate the slice, it's going to go around like that. It sweeps around the axis and comes back around, giving this washer shape. The thicknesses are dy because they're perpendicular to the y-axis. They're cutting through the y-axis. And so we're going to need to work out what is the volume of the slice, which is going to be its area times dy this time. So same as before, big circle's area minus small circle's area times dy. So now I'm going to ask you to pause this for a couple of minutes and see if you can figure out what is r big and r small as functions of y. What is the larger radius? What is the smaller radius as a function of y? So please pause here for 2 minutes. All right. So since we need functions of y, I'm going to solve these for as to make them as x equals function y. Of course, this is just x equals y. It's the same as y equals x. This is x equals square root y. So that's what that curve is. They cross, of course, at 1, 1. So the bigger radius is the distance from here to here as functions of y. So this never changes. As a function of y, this is always 2. That's this line. This over here is x equals y. So the distance from here to here is the difference between 2 and y. So that means my big radius is 2 minus y squared. Now, you might do y minus 2, which technically is wrong, because you're doing the smaller value minus the bigger one. You get a negative radius. But if you're careful, things will work out just fine, because you're going to square this. And so if you got the sign of this wrong, it wouldn't make a difference because you're squaring it. But it should be 2 minus y as the radius. That gives you a positive number. The y's over here are clearly less than 2. Now, the smaller radius is the distance from here to there as a function of y. Again, this distance is always, this y coordinate's always that. This x coordinate's always 2, but over here x is a function of y is square root y. So we get 2 minus square root y. That's this x coordinate minus x coordinate as functions of y. 2 minus root y. So that's the smaller radius. And it's a mess. It's a mess. So the volume of the slice is that times dy. Now we're going to simplify this. So I'm going to square 2 minus y. I'm going to square 2 minus root y. That's the easiest way to do this antiderivative is just to square these out and simplify. Continuing to simplify, I got 4 minus 4. Those go away. Then I have minus 4y and minus y. Notice this minus distribute, so I end up with minus 5y. These two other terms don't have anything to combine with, so I end up with y squared plus 4 root y. And that's probably the simplest form of my volume of the slice. Now I need to add them up. Where do the slices begin and end? Well, the slices start down here when y is 0, and they go up through the region, and they end up here when y is 1. I'm only comparing where the slices go. The fact that they rotate all the way out here doesn't matter, because I'm focused on the region here. So my limits of integration are y is 0 to y equals 1. Again, I will leave this as an exercise. I don't want to write it all up. When you work this out, it gets the fascinating, exciting value of pi over 2 is the volume of the solid. Anyhow, so that's it. Sub has the homework. I think it's Mr. Paimani in there today. So have fun with these. These can be tricky. Work them out carefully. Draw nice pictures. And these are due, and the homework is due tomorrow. Thanks for listening. Take care, y'all. Bye-bye.